Hi, my name is Ramsés Sánchez from the Lamarr Institute in Germany, and I would like to tell you some bits about latest contribution titled Foundation Inference Models for Markov Jump Processes, which, as you might have already guessed from the title, introduces a framework for zero-shot inference. So let me start by reminding you about Markov Jump processes, which are continuous time stochastic processes taking values in discrete state spaces, like the three-state system in the figure. Now, given some initial condition, these processes are completely characterized by the transition rates, which quantify the likelihood of movement among the states. And their realizations are piecewise constant functions of time, like this one here. Now, in reality, we only have access to noisy and sparse observations on these realizations. And the main task is how to infer the hidden transition rates from the noisy observations only. Just to give you an example, an important application of Markov jump processes deals with molecular dynamics, which feature jumps among metastable configurations. As you can see, for example, in this figure, where we record the values of the torsion angles of a simple molecule as time evolves, and which get trapped, the values get trapped in 2 times 3 metastable configurations. And now the question is, given this time series, can we infer the transition rates that best model the dynamics? Well, the classical approach to solve this problem has basically two components. First, a trainable generative model that imposes the Markov jump process prior onto the data and which treats the transition rates as trainable parameters. And second, a trainable inference model which yields the posterior distribution over the Markov jump process. Now, I would like to highlight two features of this classical paradigm. First is that it's, of course, an instance of unsupervised representation learning, simply because we never have direct access to the hidden variable. And, well, unsupervised representation learning is tricky. Second, that the model parameters are optimized to fit a single target dataset only. And this means that we have to repeat this complicated training procedure every time that we're given a new dataset, even when the underlying process of the two datasets are very similar. And our main issue with this is that we believe that many times in nature, the processes that are underlying different datasets, the Markov jump processes, are actually similar. So an alternative would be to somehow gather a large data set of different Markov jump processes. Their noise observations and their actual realizations, and then train a single inference model on all of them in a supervised way. But how can we come up with such data sets? Well, enter Foundation Inference Models, which also has two components. Then the first one is a fixed hierarchical generative model that introduces a distribution over the transition rates, and which we use to simulate a large data set of different Markov jump processes with their noisy observations. And second, a trainable inference models. Now, in contrast to the classical paradigm, our approach is trained in a supervised way because we have access to the transition rates. We simulate them. And second, that the model parameters are optimized to fit essentially or effectively multiple synthetic processes because we simulate them. And now what we show in our paper is that if the synthetic data set that we simulate is broad enough, then the framework allows for zero-shot inference of different Markov jump processes with a single pre-trained model. And indeed, we demonstrate that one and the same pre-trained model can perform zero-shot estimation of entropy production rates in systems that break time reversal symmetry, mean first passage times of experimental switching ion channel data, or stationary distributions from molecular dynamic simulations. And in this slide, I showed you the training times of a state-of-the-art baseline as compared to the zero training times of our pre-trained model, which actually performs on par with the baseline. Well, I hope I got your attention some bits, and that I will see you next December 13 during the poster presentation, where I can tell you a bit more about our proposal. Thanks for your attention.